Good morning students. Welcome to day 2 class of mathematics from class 10th of chapter 1 real numbers. Let us recall once what we might have discussed yesterday. At first we have discussed about real number system. You might have seen the chart. What are the types of real numbers? And next, division equation. And then Euclid's division lemma, given two positive numbers a and b. There exists a unique pair of integers q and r satisfying a is equal to bq plus r, where 0 is less than or equal to r less than b. And applications of Euclid's division lemma, that is, we discussed yesterday two sums based on Euclid's division lemma. And we gave some problems also to do as homework. Hope you might have completed. Right? Thank you.
Please.
Let's listen. Today's first topic is factorization theorem. What is the statement of factorization theorem? Theorems means, please don't bother about, I am not supposed to go through the proof of the theorem. So don't compare with the geometry. Okay. So we just based on the statement, and let us go through the examples also. So let us see the statement of factorization theorem. Every composite number can be expressed as a product of its prime factors in unique way, apart from the order of the prime factors occurs. Means we know very well every composite number can be expressed as the product of prime factors in an unique way. Means unique means what? In one way only. We don't want to express in so many ways. So that comes under the meaning of a unique way. Let me give some examples. Okay, listen. Example. You take a composite number 45. You take a composite number 45. Let us divide 45 as the product of prime factors first. Better you do the division at the right side. 45. Any one of you can say this number is divisible by 2. Yes, it is not divisible by 2 because 45 is not an even number. So let us go through the next number. So it is divisible by 3. 3 table 15 times. Possible. Can you say is this the 15 is possible again by 3 or not? Yes, it is divisible by 3. Now, can we write 45 as the product of prime factors? What are the prime factors here? 3 and 5. Of course, 3 was repeated as twice. 3 into 5. My sincere advice is, better you write its exponential form if necessary. If necessary in the sense, if any prime number which was multiplied by twice or thrice, then better we write it as a power notation. That means 3 square into 5. Now, from this, hope which is clear to all, I think, every composite number can be expressed as its prime factors in unique way, apart from the order the prime factors occurs. See, 45 is a composite number. Are we able to express this 45 as the product of prime factors or not? Yes. Let us go to the first problem. Find the HCF and the LCM of 24 and 84 by prime factorization method. See here, we are asking to find the LCM as well as HCF for the two given numbers. So before we have already divided 45 and we wrote as the product of prime factors. In the same way, better you write 24 and 84 also. Let us go through the solution. 24 is there. Better we divide 24. 2 table is possible. 2 12s are 22. Again 2 6 are 2 3s are. In the same way 84 also we divide. 2 table 42 times, 2 table 21 times. Can we expect 2? No. 2 is not divisible in 21. So 3 divides 21 for 7 times. Now how can we write 24 as the product of prime factors? Better we write exponential form if it is possible. Let us go through this division. 2 is multiplied thrice. So can we write 2 cube at a time? 2 cube into 3. Now go through 84. 2 is multiplied twice. 3 comes for one time and 7 also comes one time. So we might have prepared the product of prime factors in power notation. And now you see what is HCF. HCF is nothing but a product of smallest prime factors. Product of HCF is equal to product of smallest powers of each prime factor. Product of smallest powers of each prime factor. Let us see here. Here 2 comes as 3 times, but here 2 comes as 2 times. So when we compare these two, we can go to the product of smallest powers of each prime factor. Each prime factor, of course, it is not only a prime factor. We would like to say it is nothing but a common factor also. Is it clear? So I have forgotten to write. It must be a common factor in both the numbers. So here 2 comes as 2 times and here 2 comes as 3 times. So the minimum value is 2 squared. And then what is the common factor after 2? 3 is the common factor for both prime factorization. So here 3 one time and here also 3 one time. Can we write 7? Is it possible to write 7? Because 7 is not a common factor. 7 is not a common factor. So instead of 7, we don't want to write 7. Now this value we know. 2 square means 4 into 3. That is nothing but 12. So what is the highest common factor of the two given numbers is 12. Now let us see LCM. LCM is nothing but product of greatest powers of each common prime factors. Here you see, when we are writing HCF, we took smallest power, but when we are writing LCM, we must go through the greatest powers. So by comparing 2 cube and 2 square, which is greatest? Yes, 2 cube is the greatest. So I am writing 2 cube. Anyway, 3 is same. We can't take more. Here 7 was absent, but here which was present, you know. So we must take 7 also. We know the value of 2 cube. 2 cube is 8 and 3 sevens are 21. 8 ones are 8, 8 2s are 8 2s are 16. So from this we came to know the highest common factor of the two given numbers 24 and 84 is 12, and the LCM of the two given numbers is 168. Is it clear to all? Let us go through the second problem. Explain why 7 into 4 into 13 plus 13 and 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 are composite numbers. Let us take first one. 7 into 4 into 13 plus 13. See, the product of 7 into 4 into 13 is one term, and we consider plus 13 is another term. So among these, can we take 13 as common? So better we take 13 as common. So when we took 13, the rest of the terms you write it within brackets. 7 into 4 into, instead of 13, I am writing 1. Next, plus symbol is there. In place of 13, again I am writing 1. So that is equal to 13 into 7 4s are 28, 28 ones are 28 plus 1. That is equal to 13 into 29. Here we need not to multiply this product. Why? Because this entire value comes as the product of two different numbers. Is the product of two different numbers. Therefore, 7 into 4 into 13 plus 13 is a composite number. Is a composite number. See, for example, actually here what I would like to say is 3 is a prime number, 7 is a prime number. Can we expect the product is also a prime number? No, because 21 is not a prime number. It is a composite number. Why? Because it has the two factors. It is the product of two different numbers, that is 3 and 7. Now let us go to the second part of this question. 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5. Here we conclude until the product of 7 to 1 comes as one term, and the rest of the second term is plus 5 is next term. So apart this, can we take 5 as common? So take 5 common. Rest of the terms like above you write in brackets. So 7 into 6 into 5 already we took outside. Instead of 5 I am writing one time. So rest of the terms 4 into 3 into 2 into 1 plus, instead of here 5 also I am writing 1. This is equal to 5. Let us say 7 6 are 42. 42 4s are 168. 168 into 3 2s are 6. When we multiply like this, we get 1008, and still 1 is there. That is equal to 5 into 1009 is the product of two different numbers. Hence, we conclude that 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 is a composite number. Is it clear? The next topic is rational numbers and their decimal expansion. Let P by Q be a rational number where P and Q are co-primes. Here you say the statement, if Q can be written as 2 power n into 5 power n, whereas n and m are non-negative integers, then the decimal expansion of p by q will be a terminating decimal. That means when a fraction is given, that means under examination point of view, some questions will be given. That is, they may give some fractions. We are asking to verify whether they are terminating decimals or non-terminating decimals without actual division. We need not to do the actual division. So how can we say? So when a fraction is given, first of all, let us convert the given fraction in terms of its lowest terms. If it was given already in lowest terms, we need not to bother about that. Then we would like to focus on only the denominator, because if you observe p by q, q is the denominator or not? Yes. So q, are we able to write in the product form of 2 power n and 5 power n? See, for some cases we may get only 2 power n, or in some cases we may get only 5 power n, or in some other fractions the denominator we may write it as the product of 2 powers as well as 5 powers also. In all these conditions, the given fractions are said to be a terminating decimal. So except 2 and 5, the other numbers, means other prime numbers, maybe 3 or 7 or 11 or 13, some other numbers comes in the denominator, we should say that is not a terminating decimal. Simply it is non-terminating decimal. That means here one thing we should try to inject in our mind. When we go through the denominator, that means when we write as the product of its prime factors, the product of prime factors must be only 2 powers or only 5 powers or both the powers of 2 and 5. Except 2 and 5, if any number is present in the product of prime factors, it is blindly we should say it is a non-terminating decimal. Let us go through a problem what we discuss in the above. State which are terminating and which are non-terminating of the following fractions. Here 3 questions were given. A 37 by 12, B 13 by 3125, C 64 by 455. Let us go through the solutions one after one. Let us see solutions for A 37 by 12, which is a fraction, which is in the form of P by Q. Of course, P and Q are co-primes. Can we do the simplification? Still? No, because already 37 by 12 which was given in the lowest terms. Now let us go through Q. The value of Q is 12. How can we written as 12? But we will do the division. 2 table in 12, 6 times possible. Again we divide it to, it is 3 times possible. So now the denominator Q can be written as 2 square into 3. If you observe the explanation carefully, the denominator, that means the value of Q, must be in the form of 2 power n and 5 power n. If only 2 is present, the given fraction is a terminating decimal. If only 5 is present, the given fraction is a terminating decimal. If both are present also, the given fraction is a terminating decimal. Unless 2 and 5, if any one of the prime factor comes in the product of prime factors, it is not a terminating decimal. See here, it is not in the form of 2 power n into 5 power n. Therefore, 37 by 12 is not a terminating decimal. Is not a terminating decimal. Let us go through the second one. Of course, which is also is in the form of P by Q. So we need not to do the simplification. So no number is possible in both. From this we came to know the value of Q is 3125. So divide 3125 as the product of prime factors. See 3125. Can we say 3125 is divisible by 3 table? We know the test of divisibility. If a number is divisible by 3, sum of all digits is divisible by 3. 3 plus 1, 4. 4 plus 2, 6. 6 plus 5, 11. Usually we may expect if one's place is 5, there is a chance that number is divisible by 3. So here it is clear. Sum of all the digits is 11. So 11 is not divisible by 3. No? So we are sure that this number is divisible by 5. 5 6 times. 5 6 are 30. 5 2 are 10. Still 25 is there. 5 5 are 25. Now again you see whether is there any chance this number is divisible by 3 or not. 6 plus 2 8. 8 plus 5 is 13. 13 is not divisible by 3. So better we go through 5. 5 125 times possible. Again 5 25 times possible. Again 5 5 times possible. Now 3125 can be written as 1 2 3 4 5. 5 power 5. That means here you see, don't expect for each and every question along with 5 2 also may present. For some questions 2 may present, and for some questions 5 is only present, and for some questions both 5 and 2 also may present. So here I am writing, since Q is in the form of 2 power n into 5 power n. Here some students may ask a question. Sir, how can you say this 3125 is in the form of 2 power n into 5 power m? Why? Because here 2 is not present, in the product of prime factors. How can you say Q is in the form of 2 power n into 5 power m? Means here one simple thing is there. Can we write 3125 as 3125 into 1? Yes. What is the value of 3125? Actually here 5 power 5. Instead of 1, can we write 2 power 0? Means if 2 power 5 is 5 power 5 is there, means we should expect 2 power is also present. Why? Because we can write 3125 as the product of 3125 into 1. Instead of 1, I am writing 2 power 0. Now this expansion is in the form of 2 power n into 5 power n. Of course, n value is 0. We need not to bother about it. Therefore, 13 by 3125 is a terminating decimal. Is a terminating. Is terminating. Let us go through the last one. 64 by 455, which is in the form of P by Q. The value of Q is 455. So now again 455 I would like to divide with either 3 or 6. Is this number is divisible by 3? Is it possible? Let us go through the test of divisibility. 5 plus 5 plus 4 is 14. Sum of all digits is not divisible by 3. So that is the case. Better we go through the 5 division. 5 8s are, 5 9s are 45. 5 1s are 5. Now here 91 is there. Can we expect the division is possible maybe with 5 or 3? No. So here the division is possible with seventh table, 7 13 times. So Q can be written as 5 into 7 into 13. Let us go through the first sum. Here, along with the 2 power, we get 3 also. So unless 2 and 5, if any one of the number which was present under the product of prime factors, it is clear which is not a terminating. Okay, here 5 is present. Of course 2 was absent. But unless 2 and 5, if any numbers are present, it is very clear it is not a terminating decimal. Q is not in the form of 2 power n into 5 power n. Why? Because the presence of 7 and 13. Therefore, 64 by 455 is not terminating. Next question is, write the following rational numbers in decimal form without actual division. Means we need not to do the division. So without actual division, are we able to say their decimal fractions are not? Let us see the explanation part. Solution of first sum. 143 by 110. So can we write 143 as the product of two numbers, that is 11 into 13. And the denominator 110 I am writing as 11 into 10. So 11 will be cancelled. So what the value is left? 13 by 10 is left. So without doing actual division, are we able to write this decimal fraction or not? Yes, its value is 1.2. How it is possible? If we observe the denominator 10, here both 2 and 5 are present. Can we write 10 as the product of 2 into 5? That means both 2 and 5 are present in this denominator. So that is the reason we are able to write its decimal value without actual division. In the same way, do the division for 7218 by 3 square into 5 square. 7218. What is the value of 3 square? 9. You need not to find the value of 5 square. You leave like that only. Let us do the simplification with the 9 table. 9. 9 8s are 72. Now 0 times 9 8s are 72. 0 times 2 7. 9 2s are 80. So, but don't write a mistake here. 82 times. That is 802 times. It is possible. So the value of this is 802 by 5 square. What I am doing to get a decimal expansion? Anyway, because here 5 is multiplied for 2 times. So that is the case. This entire fraction 802 by 5 square I would like to multiply with 2 table. Since the power of 5 is 2, I would like to multiply with 2 power 2 only. Here 5 power 3 is there. So what should I multiply? To cube I have to multiply. Here 5 power 4 is there. What I would like to multiply here? 2 power 5. So multiply and divide with the 2 square. What will happen? You see. 802 into 2 square means 4 by 5 square means 25. 2 square means 4. This is 80 for x are 32 divided by 100. We know very well, if the denominator is 10 or 10 powers without doing actual division, we are able to write its decimal fractions. How? If you go to the first example, if you observe in denominator 10, only 1 0 is there. So that is the case from the right side onwards. After one digit, we kept a decimal, and here you see 2 zeros are there. So what can I do now? After 2 digits from the right side, you want to keep a decimal point. So the rest of the values as usual you write. Now the decimal fractions of 143 by 110